last lesson in our unit, and if the video doesn't go too long, I'll just keep it as one video, and if I keep talking for a little bit longer than expected, then I'll break it into two. But it's our last day of unit number 1, and I always say it's kind of fun to get to this point because we're actually now at the point where I'm going to start to teach you something new. Okay, everything up to now maybe was review from grade 11, depending on how your year went last year. So this is where we get to take some of this basic chemistry understanding and then apply it to the shape of a molecule. Okay, so how is it that we understand that when we're looking at molecules, that if there are 4 things bonded to one center atom, it's going to rearrange itself to be in this shape. So you know that when you get your molecule kits, if you're building water, you just simply grab 1 oxygen and 2 hydrogens and you put it together. Well, funny enough, this oxygen is made to represent the fact that there are 2 bonded pairs of electrons to the hydrogens, and then there's 2 lone pairs of electrons that would be up here, but there's simply no spot for those bonds to go on these molecule kits, right? So it's kind of interesting that it's built this way. It's built this way because this is the actual shape of that molecule. And I'll turn it to this one. You certainly know this is methane, and it's a carbon atom that's in the center. Well, when you pick it out of the molecule kit, you'll realize that there are 4 little spaces for the bonds to go. They're equally spaced all the way around, and so when you build methane back in grade 10, probably when you did your molecule kit, you grabbed 1 carbon and 4 hydrogens and you had just put it together. Well, understand that it's based on this thing called the VSEPR theory. Okay, so it's looking at the shape of a molecule based on how many pairs of electrons are around a center atom, and we recognize the fact that these are electron clouds. So we know that an electron cloud has a negative charge, and so can you picture the fact that there's electrons at each of these bond points? And if something has the same charge, they're going to want to repel each other as best as they can. And this is the basic understanding of the VSEPR theory. Okay, so here we go. I filled the first part in. We're going to cover pages 39 to 43. But please make sure that, you try this on your own first before you certainly check the solutions. The whole point here is that you think that VSEPR actually stands for the valence shell electron pair repulsion theory. So I want you to memorize all the words that make up that little acronym, okay? And I know that even though the E comes after the S, chemists will still just say VSEPR theory because it sounds better than trying to put the S first and then the E. Okay? All right. So then we understand we've got some valence electrons. We understand that those electrons have a negative charge. We understand that we're dealing with covalent bonds because these are molecules, are molecular aggregates. And we understand that when there's a negative region, like I've already mentioned, it's going to repel another negative region. Okay? And so the VSEPR theory basically says that because of this repulsion, this is going to determine the overall shape that the molecule has. Oh, and that's funny that I've just got carbon with our 4 hydrogens right here. So that shows methane, and it shows those overlapping electron clouds where I have my 4 covalent bonds inside of that molecule. Okay? There they are. Now, there are 5 basic shapes for the VSEPR theory, and so the textbook section on this is really quite good. There's also a PhET simulation that we're going to do where you can build a molecule. I'm going to show you how to do that, and you're going to be doing some building on your own. If you have a molecule kit, you're lucky. If you don't, you're going to have to find yourself something at home in your kitchen maybe where you can build molecules. Do you have pom-poms? Do you have marshmallows? Do you have gumdrops and toothpicks? I'm going to get you to build some shapes, and there's 5 basic shapes. Okay, so not only do you want to know what the shapes are called, you're also going to be looking at what we call the dimensional diagram, and we're going to factor in a little bit of geometry here where you're going to be adding in the bond angles. Okay, so here we go. If you have a center atom and it has 2 bonds on each side, you'll notice that I happen to have carbon dioxide here, but you certainly could be looking at beryllium difluoride. Same, it's going to give you a shape that looks like this. Okay, this is a nice easy one. It's called a linear shape. It's in a line. Okay, so starting off with an easy one, linear. What are the bond angles? Well, that is 180 degrees. That's shape number one. Shape number two. What if you have three things surrounding a center atom? This is how, no matter how you look at this molecule, because remember it's a three-dimensional shape, so you're going to have to watch some animations, or you're going to have to build it and move it around. No matter how you arrange this molecule, these three electron pairs are going to be as far apart from each other as possible. And if there are three things bonded to a center atom, 1, 2, 3, the name of this is called Trigonal Planar. And the bond angle, that's easy as well, 120 degrees. So the geometry that we're doing here, the math and the angles, actually isn't too tricky. All right, moving on to number 3, and this is the one that I'm sure your science teachers have been talking about for years now. This is a characteristic shape where you have 4 things. It's called a tetrahedral. And the bond angles are all 109.5 degrees. And again, they are spaced as equally apart as possible. Okay? Maximum space, minimal repulsion, and spaced out in around, you've got 109.5 degrees. All right, what if you have 5 things bonded around a center atom? Because again, remember, we're dealing with this center atom. How many things are around it? That's the shape of this molecule right here. So let's see. Here I have 5. 1, 2, 3 on one plane. Can you see that? Where should I put it? Right there. No, here. Okay, 3 things on one plane, 2 on the other. Okay, this is called Trigonal Bipyramidal. Okay, and where does that name come from? Well, it comes from the fact that if you were to think of this as a geometric shape, and there's an animation I'm going to show you that sort of puts the faces onto this geometric shape. If you think of this as one face of the outside of this molecule, on the top you've got 1, 2, 3 trigonal, and you've got the same 3 faces that would be on the bottom. Okay, so if you think of it like this, with 3 on one and 2 on the other, there are 2 pyramid shapes, and they're in the shape of a triangle, because that's the shape you will get. You'll have 3 things on one plane, 2 on the other, 5 things bonded to the center atom, trigonal bipyramidal. Okay, last one. Are you ready for this one? You've never been able to build anything with these, because these aren't usually the examples we do in grade 9, 10, or 11. Can you see this? We've got 4 bonds on one face, 2 on the other. So I have 1, 2, 3, 4, 5, 6 things bonded. Oh, I didn't put the angles, but we'll go back and do that. This is an octahedral. Okay, octahedral. And again, if you were to put a face on here, you'd have 1, 2, 3, 4 on the top and 4 on the bottom. So that's where the octahedral term comes from, or the prefix, the octa. All right, let's do some bond angles. So for this one, because I already have it right open, the angle between this face, or this plane, and this plane is a nice easy one, 90 degrees. It'll come up in just a second. There's a bit of a delay. And then the angles between here, what are these guys? Well, they're also 90 degrees, right? Okay, it's hard to draw. I'm going to show you how to draw this on the next page so you can draw a diagram that has a bit of dimension to it. Let's go back to the one that had 5 things bonded to a center atom. These guys, and this plane here is obviously a 90-degree angle. And then if you have 3 things on one plane, you remember what the angle is between 3? Of course, it's 120 degrees. Okay, so let's move on. Do I have all the angles? Everything's good to go? Okay, so you're going to review those 5 shapes, and I want to show you on the PhET simulation what you're going to do. You're going to go into the link, and you're going to click on the model. From the model, you can take this molecule, and you can simply spin it around. Okay? all you need to do is add on or subtract how many bonds. So if I have two things, you can see that that's going to be a linear shape. Okay, I'm just going to click on this one and the answer will come up here. I haven't taught you how to do the second part quite yet. What if I had another bond? Add another one, 3. And if you want to check to see the bond angles, well, I can first of all move it around so you can see, right? 3 things bonded to the central atom. Do you remember the name of that one? Trigonal planar. Show the bond angles, 120 degrees. Let's add 4 things. You remember what's going to happen if you have 4 things bonded to it? You've got yourself a tetrahedral, which is 109.5 degrees. Let's add another one. You can see there. I'll spin it around. This is actually a really neat little simulation, okay? It'll catch up, and then you can see that the angles all bond, or the bond angles all sort of align themselves. And the last one are octahedral. Okay, so I want you to play around with that simulation as you fill in your note. Let's have a look at the next page. So, as we review, right, the acronym for VSEPR stands for the valence shell, electron pair, repulsion, and it's a theory. It has to do with the shape of the bond pairs, and it also has to do with the fact that sometimes you have a molecule like this one where there are some lone pairs of electrons around a center atom. Okay, so we're at this point here, we're moving into the next step where we've got to look at the shape of the molecule that's determined by not only how many bonded pairs, but how many lone pairs of electrons we're going to have. Okay, once determined, because the electron pairs, remember, have a negative charge, adjacent electron pairs will repel, so they're as far apart as possible. And when electron pairs have the maximum distance between themselves, that's a key term, maximum distance between themselves, the repulsion is minimized. And what happens is the most stable shape of the molecule results. So VSEPR theory works if you're trying to predict the shape of any of these molecules that we build with our molecule kit because they are covalent. So remember how I've said that, the ionic ones are pretty easy, right? The names of the bonds are easy. The intra and intermolecular bonds are all called ionic. When we're looking at the covalent molecules, right, all of a sudden things start to become trickier with regards to the nomenclature of them, trickier with regards to thinking about if the intramolecular bonds are polar or non-polar, and then what about the polarity of the molecule itself? So then you're looking at the intermolecular bonds, right? Are they instantaneous dipole, 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 or hydrogen bonding? And now it's like, all right, well now let's figure out what if I have some lone pairs as well as some bonded pairs. How do I take that line diagram and actually show the shape of the molecule? Because not only is it going to be the polarity of the molecule that factors in, but once we know the actual shape of the molecule, that can also affect the polarity of the molecule. Okay, so there's a lot of factors that come into play, but this is really the fun part of it, where you get to build some shapes and look at the geometry and basically figure out what it looks like. Okay, so here we go. Let's look at the second part here, where I'm going to show you how to do the diagrams. I'm going to show you just how to draw this so that you know what the shape of the molecule is, and then we're going to do the dimensional diagram with the bond angles. Okay, so the first one's easy. What if I have 2 pairs of electrons around something? Okay, an example AB2, we're just going to give an example here. Do I have a molecule? Oh, I could give you a molecule to do. The shape is going to be linear. Let's just draw that, okay? I'm going to use beryllium difluoride because that's what we had on the first page. That's all you're going to draw. You're going to add in your bond angles. And of course, if it's linear, that is easy. It's 180 degrees, okay? Let's draw the next one, trigonal planar. It's also easy because it's in the same plane, right? Let's do an example of BF3 because that's what we had on the previous page. B, F, F, and F, and my angle is 120 degrees, okay? They're all on the same plane. All of a sudden, when you get to the tetrahedron, we know that we have to draw this to give it a little bit of dimension, and here's how you start. You start with your center atom, and I start with two that are on the same face or the same plane. I'm not sure if you can see that. It doesn't matter which two you start with. I'm going to start with the ones on the left. So I start with my center atom, and I draw two that are on the same plane, so just one little line with no dimension. Let's do methane, because that's the easiest one. And then if I'm looking at this methane molecule, I need to draw one of these bonds of the hydrogen coming towards me and one going away. All right, so how do we draw that? We simply draw a little triangle that's filled in. That's the coming towards, and that's the going away. Fancy. Some of you are going to be way better at drawing some organic molecules than me. But it's the practice that counts, I guess, yes. And our angle, again, 109.5 degrees. Okay? Next one, trigonal bipyramidal. So I'm going to start with my molecule that I had from before. That's this one right here. I'm going to draw it with an up and a down on the same plane. Okay? And I'm going to tilt it so that one of these of the three that are on this plane are in line with the two that are up above. I'm not even sure if you can really see how I'm doing that, but I'm going to draw it and you're going to see what it looks like, and then you can try it at your house, okay? So let's do some chlorines. There's a chlorine, there's a chlorine, and there's a chlorine. And then what I need to do is I need to reflect that these two on the same plane, one's coming towards me and one's going away from me. So you're going to draw your triangle like this. There's my chlorine there, and there's my chlorine there. And it kind of looks three-dimensional. Let's add in our bond angles. Okay, between here and here was our 90 degrees, and between these on this plane was 120 degrees. Do you need to put it in for each single one? No, that's good enough. Okay, last ones are octahedral, and here's how you're going to draw this one. I'm going to take the 4 and arrange it so that I've got two coming towards me, two going away, sorry, and then I've got the plane going up and down. All right, so let's draw it this way. I'll start with my sulfur in the center. And then I'm going to have fluorine and fluorine. And then I'm going to draw two on the middle plane coming towards me. Okay. And then two on another plane that looks like they're going away. And that's as good as you can get. All right, let's add in the bond angles because I know that it doesn't really look like it, but between here and here is a 90 degrees, and between here and here is 90 degrees. Okay, so I'm going to stop this right here, and then I'm going to do the next video where we're going to look at predicting the shape if we start factoring in some lone pairs of electrons as opposed to a bonded pair of electrons. Okay, good luck.